Greetings and welcome to the 8th episode of PHS Physics SOS. Today I'm going to be going over the bookwork for Chapter 4 on forces. And I'm going to apologize for this video being a bit late. I have had a lot of computer issues this week, but I got them all sorted out, and hopefully I should be back on schedule with everything. And hopefully this should still be up tonight before the quiz so you guys can get some use out of it. But let's get started. The first question on page 145. Says, once the crate is in motion, a horizontal force of 53, and this is referring to a crate that's mentioned in a example problem up above, and it weighs 24 kilograms, which is all you really need to know about it. So the problem says, once the crate is in motion, a horizontal force of 53 newtons keeps the crate moving with a constant velocity. Find mu sub k, the coefficient of kinetic friction between the crate and the floor. So this is problem 1, and the first thing we're going to do is draw a free body diagram. So we got our force of gravity, our normal force, our applied force, and our frictional force. So our gravity is equal to our normal force is equal to mass times gravity, which is equal to, let's see, okay, and for this video, I'm going to be using, oh, whoa, you can't really see that, can you? Okay, for this video, I'm going to be using G equals 10 meters per second squared, just to simplify calculations. You're going to get answers that are a little off, but as far as I know, Ms. Casey O'Brien's okay with you using that on the quiz. So this is going to be equal to mass, which is 24 kilograms, times 10, which is going to be equal to 240 newtons. So that's, this equals 240, this equals 240. They give you the applied force, which is equal to 53 newtons. And it wants to know what's the coefficient of kinetic friction. So it's moving at, it tells you that it's moving at a constant velocity, which means if your velocity is constant, your acceleration is 0, which means your net force, which is equal to mass times acceleration, is going to be equal to 0. So since our net force is equal to 0, then all these forces have to balance out. And I drew this a little misleadingly because the applied force vector is a little bigger than the friction vector, and they should be balancing out. So we know, because it's not moving up and down, that these two are going to balance out, the normal force and the gravity. And since we said the net force is 0, that means the only other two forces that there are that have to balance out are the applied force and the force of friction. So applied force has to equal force of friction, and applied force is equal to 53 newtons, which equals our force of friction, which is our kinetic coefficient of friction, mu sub k, times our normal force, which is 240 newtons. So if you divide this over, you get 53 over 240 equals our kinetic coefficient of friction, which is 0.22. And since it's a coefficient, it's just 0.22. There's no units. Coefficients of friction have no units on them. The next question is question 2, which says a museum curator moves artifacts into place on many different display surfaces. Use the values in table 4-2 to find the max static force of friction and the max kinetic force of friction for the following situations. And part A says moving a 145 kilogram aluminum sculpture across a horizontal steel platform. And if we go and look, actually here, so go over here for 2A. If we go and look at the table on the previous page, it gives values for aluminum on, let's see, aluminum on steel. Gives you our static coefficient to be 0.61 and our kinetic coefficient to be 0.47. So next thing, to find force of friction, since we know that F equals mu times your normal force, which you can write as F sub n or just n. I like to use F sub n because if you just use n, you can get confused with the units, newtons, which can lead to some lead to some, hang on, I have autofocus on. I don't want autofocus on, sorry about that. Which can lead to some problems. Like, you don't know, is this a variable, is this a unit, and you can screw yourself up. So, the next thing we need to know is our normal force, which equals mg, which, since our mass is 145, it's just going to be 1,450 newtons, because I'm just using 10 for g. So to find our static max, it's just going to be our static coefficient of friction times our normal force, which will give you 880 newtons or so. And then to find our kinetic friction, we want to use our normal force times our kinetic coefficient of friction, so 0.47 times 1,450, which will give you 680 newtons. Now for part B, it says pulling a 14 kilogram steel sword across a horizontal steel shield. So all you need to take out of this is 15 kilograms and steel on steel. So if we look over in our table again, it'll give you our coefficients for steel, which are for static 0.74 and for kinetic 0.57. So then we need to find our normal force, which again is going to be equal to the force of gravity, which is mg, which will be, let's see, 15, so 150 newtons. And then to find our static max, we want to use, let's see, 0.74, our coefficient of static friction, times our normal force, 150 newtons, to give us 110 newtons. And for our kinetic force of friction, it's going to be equal to our kinetic coefficient times our normal force. Because remember, force of friction is always just going to be your coefficient of friction times your normal force. And when you plug that in, you get 86 newtons. Next part is part C, which says pushing a 227 kilogram wood bed on a wood floor. So again, all you need to take out of this is 227 kilograms and wood on wood. So again, if we go and look over at our table of constants, it'll give us for wood on wood 0.4 and 0.2. So again, calculate our normal force, which is the same as gravity, which is mg, which is the same, which is 2270 newtons. So for our static max, it's just going to be the coefficient of, did I write these backwards? I did. My bad, I'm sorry. So it's just going to be our static max times our, what am I doing? Our static max, which is 0.40, times our normal force, which is 2270, which will give us 908 newtons. I guess I should have rounded to another sig fig, or one less sig fig, whatever. And our kinetic force of friction is going to be our kinetic coefficient of friction, again times our normal force, which is going to give us 454 newtons. Let's see if we can squeeze part D on this same page. And then, ooh, you really can't see this edge, can you? Okay, I'll have to work on that. I'm using a bit of a new setup here, so hope it's still, everything's all seeable. So part D says sliding a 0.55 kilogram glass amulet on a glass display case. Again, the only thing you need to take out of this is 0.55 kilograms and glass on glass. So we look at our coefficients again, and we get that our static coefficient is 0.90, and that our kinetic coefficient is 0.40. So next we need to calculate our normal force, which is going to be equal to the force of gravity, which is just mass times the acceleration due to gravity, which will be 0.55 times 10, which is 5.5 newtons. So for our static max, it's going to be 0.9 times 5.5, which will give us 5.0 newtons. And then for our kinetic, I'm going to multiply our kinetic, this kinetic coefficient times our, I'm really running out of room, aren't I? Times 0.5, or 5.5. Sorry, you probably can't see that. I'll rewrite it. Equals 0.40 times 5.5 newtons. So that's going to give us 2.2 newtons. The next question is question 3, which says a 25 kilogram chair initially at rest on a horizontal floor requires 365 newtons. Requires a 365 Newton horizontal force to set it in motion. Once the chair is in motion, a 327 Newton horizontal force keeps it moving at a constant velocity. In other words, what that's telling you is it takes a 365 Newton horizontal force, the first force it gives you, to set it in motion, which means to overcome the force of static friction. And then a 327 Newton force to keep it moving at a constant velocity means that's going to be equal to your force of kinetic friction. And as you can probably assume from reading that and what I just said, part A says find the coefficient of static friction between the chair and the floor, and part B says find the coefficient of kinetic friction between the chair and the floor. So for part A, I'm going to draw our free body diagram, which is our mass, our force of gravity down, which is, let's see, it's a 25 kilogram chair, so 250 newtons. And then our normal force up, which is also going to be 250 newtons. And then our applied force, which is 365 newtons. And then our force of friction, our force of friction static. And to solve, and we know that our force of static friction is going to be equal to 365 newtons at its max. So this should be F static max. Because in the problem it tells you that that's the amount of force required to set it in motion. In other words, to just initially get it moving. So we want to set our coefficient of static friction times our normal force equal to 365 newtons. And our normal force, as we know, is 250 newtons. So our coefficient of static friction equals 365 over 250, which is 1.5. Should be static. And then for part B, it's the same chair. So it's got the same weight down, same normal force up, except the applied force this time is only 327 newtons. And it's moving at a constant velocity, which again means net force is going to be 0. So our force of friction, that's kinetic, is going to be equal to the applied force. Because, again, velocity is constant, therefore acceleration is 0. Therefore, your net force, which is equal to ma, is going to be equal to 0. Hang on, can you still see that? No, you cannot. Let's try that again. So, if your velocity is constant, your acceleration means your acceleration is 0, which means your net force, which is equal to ma, is going to be equal to 0, because 0 acceleration means 0 net force. And it means all your forces have to balance out. So our normal force balances out with our gravity, and that means, so the only two things left are our applied force and our frictional force. So these two have to cancel out, which means they have to be equal. So our force of kinetic friction has to be equal to our applied force. So our kinetic coefficient of friction times our normal force has to be equal to our applied force. And since we're looking for our coefficient of friction, we just plug the normal force in. Divide this over, and we get that our kinetic coefficient of friction equals 327 over 250, which equals, where is it? Ooh, there's a spider on my microphone. Hello, spider. No more spider. Sorry, which is equal to 1.3. The next question is question 1 on page 147, which says a box of books. Let's partition this off. A box of books weighing 325 newtons moves with a constant velocity across the floor when it is pushed with a force of 425 newtons exerted downwards at an angle of 35.2 degrees below the horizontal. Find mu sub k, the coefficient of kinetic friction between the box and the floor. Okay, so start off by drawing a free body diagram. So we have our box, which weighs 325 newtons. We have an applied force downwards of 425 newtons at an angle of 35.2 degrees. Now, you'd be inclined to think that the normal force is just going to be 325 newtons up, but since this is pulling somewhat downwards as well as forwards, the normal force is actually going to be more, because there's more than just gravity pushing down, and whatever surface this is on has to return all the force pushing down. So it has to return the force of gravity and the downward component of this applied force. So to find that downward component, we need to use a little bit of trig. So we want to separate this into our x component. So this is going to be our applied force in the x direction and our applied force in the y direction. 35.2, 425. So to find our x component, it's going to be 425 cosine of 35.2, which is going to be equal to 347 newtons. So that's this component. And then our force in the y direction is going to be equal to 425 sine of 35.2, which is going to be equal to 245 newtons. So now we know x component and our y component. So that's the first thing you want to do whenever you have a problem with an angle like this, is split it up into its x and y components. So now we have this force of 245 newtons as well as the weight pulling down. So now we're going to redraw our free body diagram, and the total force pulling down is going to be force of gravity plus the applied force in the y direction, which in total is going to be 245 plus 325, which I believe, if I did my math right, is 570 newtons. So that means our upward force, our normal force, exerted by the table or whatever this is on has to be equal in magnitude to this force, so this is also going to be 570 newtons. And our pull forward, our applied force, the x direction, as we figured out, is 347 newtons. And the problem is asking for the coefficient of kinetic friction. Again, it's moving at a constant velocity, which means our net force is 0, which means all of these have to cancel. So since net force is equal to 0, all forces must cancel out. This is an important concept. So the normal force and the gravity cancel or the normal force and the gravity plus the downward force from the applied force, the downward component of the y force, have to cancel. So those cancel. But then the frictional component, the force of friction, the force of kinetic friction, has to be equal to the applied force in the x direction. So our force of friction, our force of kinetic friction, has to be equal to our applied force in the x direction. So we know our applied force in the x direction is 347 newtons, and we know that friction is equal to mu times normal force, and we know our normal force is 570 newtons. So, and since it's moving, we know it's a kinetic coefficient of friction. So our kinetic coefficient of friction times 570 has to equal 347. So our kinetic coefficient of friction equals 347 over 570, which is equal to, drumroll, 0.609. Ain't that a problem? The next question is question 2 on page 147, which reads, a student moves a box of books down the hall by pulling a rope attached to the box. The student pulls with the force of 185 newtons at an angle of 25 degrees above the horizontal. The box has a mass of 35 kilograms, and the coefficient of kinetic friction between the box and the floor is 0.27. Find the acceleration of the box. Okay, so start off with a preliminary free body diagram, which is going to have a downward force of gravity, which is just, and it gives you mass equals 35 kilograms. So our downward force of gravity is going to be 350 newtons, because I'm just using g equals 10 to make it easy. And then we know that we have 185 newtons pulling upwards at an angle of 25 degrees. So the first thing we want to do is split this into its component forces. So we're going to call this our applied force. We'll call it F sub A equals 185 newtons. And we want to split it into its x component and its y component. So to do that, we're going to use a little bit of trig. So F, our applied force in the x direction, equals, that looks like a 28, isn't it? That should be a 25. 185 cosine 25, which is going to be equal to, I don't know, 73 newtons. And then, that can't be right. And it is in fact not right. I don't know, I think that's something else. I had it written down. It is 168 newtons. And our applied force in the y direction is equal to 185 sine of 25 degrees. And that is equal to 78 newtons. I don't know where that 73 came from. So now we're going to redraw our free body diagram. And we know that the upward force, the total upward force, has to be equal to the total downward force, because it's not moving up or down. What is this? The box of books is not moving up or down. It's just sliding horizontally along a table. So the total upward force So the downward force is 350 newtons, but the total upward force also has to be equal to 350 newtons. But it's composed of the normal force and the upward force of this box, or the upward force of the applied force, which is 78 newtons. I guess I should have written what that was. Yeah, the y component of that force. So, to calculate what the actual normal force is, the actual force exerted by the table, because the upward force that's being exerted by the rope that's pulling the box, this upward force is not part of the normal force. It just happens to be pulling it up as well. The normal force is what's left over that has to be equal to the mass. What's left over that adds up to be equal to the mass. So 350 equals normal force plus 78 newtons. So 350 minus 78 equals our normal force, which is equal to 272 newtons. And that's not the answer to the problem, that's just important, so I put it in a box. And it says the coefficient U of k, the kinetic coefficient of friction U of k, mu of k, is 0.27, so that means our frictional force backwards is, kinetic friction is going to be equal to 272 times our kinetic coefficient of friction, so our normal force times the coefficient of friction, which is going to be equal to 73. So now, for the final part of the problem, to find the actual acceleration of the box, we need to find our net force. So to find that, we need to take our forward moving force minus our backwards moving force, because these two already balance out, the upward force and the downward force. So all we're dealing with is the forward force and the backward force. So we're going to take 168 minus 73. So that's this force minus, I guess I should have written that in there, minus this force. And that's going to give us 95 newtons, which is our net force. And to find our acceleration, we want to take that and divide it by our mass. So this is 95 newtons over 35 kilograms, which is going to give us a net acceleration of 2.7 meters per second squared. The book says 2.9. I'm not really sure how they got that. Maybe it's because I'm using 10 for gravity and they're maybe using 9.8 or whatever, or some sig figs issue. But if you're around there and you follow these steps, you're fine. The next question is question 4. And this question is actually more of an AP style question. So it reads, a 75 kilogram box slides down a 25-degree ramp with an acceleration of 3.6 meters per second squared. And part A says, find mu sub k, the coefficient of kinetic friction between the box and the ramp. And at first glance, this seems like a very daunting problem, and admittedly it somewhat is. But start off by just drawing a picture, draw your box, draw your force of gravity. So since the mass is 75 kilograms, we know that the force of gravity is going to be 750 newtons. Oh, and this is 25 degrees. So and we want to calculate, when you're dealing with ramps, the first thing you want to do is split things up, split this force of gravity up in terms of perpendicular and parallel forces to the ramp. So you want to split it up into a force of gravity that's perpendicular to the ramp and a force of gravity that's parallel to the ramp. So when you do this, you end up with a triangle, and this angle up here is the same as this angle over here. So I'm going to pull this out. That's terrible. So we have 750 newtons over here, 25 degrees up here, and this is our gravity, and we want to know our force of gravity perpendicular to the ramp, and our force of gravity parallel to the ramp. So to figure that out, we're going to use a little bit of trig. So this, the force of gravity perpendicular to the ramp, is going to be 750 cosine 25, which is going to be equal to 680 newtons. And then the force of gravity parallel to the ramp is going to be 750 sine 25 degrees, which is going to be 317 newtons. Now, it says the box slides down the ramp with an acceleration of 3.6 meters per second squared. So if we know that our acceleration is 3.6 meters per second squared, then we know that our net force, which is equal to mass times acceleration, is going to be equal to 75 times 3.6, which is equal to 270 newtons. So now that we know our net acceleration and we split these apart, I guess I kind of did this out of order, but I'm going to redraw this free body diagram with these forces on it, and I'm going to figure out what we can do with this net force. I mean, you never draw a net force on a free body diagram, but we're going to see what it equals on the free body diagram. So we'll redraw this. So we have 680 newtons pulling perpendicular to the ramp, which means we also have a normal force. Remember, normal means perpendicular, and this is just a little mathematical symbol for perpendicular. It's a little right angle symbol that you see in a right triangle. So the normal force is also going to be equal to that because the block is only going down the ramp. If these two forces didn't balance out, that would mean that it's accelerating either off the ramp or into the ramp, which doesn't make any sense because it's just going perfectly parallel to the ramp, meaning there can be no net force in the direction perpendicular to the ramp. So these two have to cancel out, meaning the normal force of the ramp on the box has to be equal to the component of the weight of the box that is perpendicular to the ramp. In other words, this. The force of gravity that's acting perpendicular to the ramp. So we also know that the force of gravity acting down the ramp is 317 newtons. That's this. And we know that our net force is 270 newtons. So that means these two forces cancel out, so we're ignoring these. So all we have left to look at is this force. Now there must be something against it, acting against it, because it's greater than 270. And that force acting against it is going to be our force of friction. So we know that, so our net force has to be equal to 317 minus our force of friction, because the force of friction is acting in the opposite direction of the downward component of gravity. Remember this. So that net force, 270 newtons, minus 317 equals our negative force of friction. I guess I could have done that better to make it positive, but let's see. 270 minus 317, so negative 47 newtons equals negative force of friction, and cancel the negative signs. So 47 equals our force of friction, but they're asking for the coefficient of kinetic friction, and since we know that friction equals mu times normal force, and we know our normal force, we can figure out this. So 47 is equal to our force of friction, which is mu times normal force. So 47 equals kinetic mu times 680. So 47 over 680 equals our kinetic coefficient of friction, which turns out to be 0.07. Ain't that a problem? Now, that's more of an AP problem. You're probably not going to see something like this on a quiz. You might see it in parts, or you might see parts of it, but just from this problem, they give you the weight, they give you the angle, find the coefficient of friction. You're not going to see that in one step. It'll be a multi-step problem. The next part of that question is part B, which asks, what acceleration would a 175 kilogram box have on this ramp? Now, this is a bit of a trick question because when I first did it, I redrew all the forces, I redrew the whole free body diagram, I split up the weight, and I figured out the acceleration. And it's equal to the acceleration of this. It's equal to 3.6. And when you step back for a second, that makes sense because the acceleration due to gravity for all things is going to be the same. I mean, this was something Galileo discovered, and of course we've talked about. If I drop a heavy tape dispenser or a pen, they're going to fall at the same rate. Now, that's not going to change if I slide something down a ramp as long as it's the same ramp at the same angle. So if I slide a big object and a small object down a ramp, as long as they're experiencing the same coefficient of friction, and as long as we're ignoring air drag, you're going to have the same acceleration. So the answer to part B is 3.6 meters per second squared. Now, you could redraw it, this time you have a big mass of, a big weight of 1,750, actually no, 1,750 newtons, and you could split it up into 1,600 newtons and 740 newtons. Again, this is your normal force at 1,600 newtons. You multiply that by this, you multiply your normal force by your coefficient of kinetic friction, and you get your frictional force of 110 newtons. You subtract these to get your net force because this cancels. So you subtract these two to get your net force, which turns out to be 630 newtons. You divide by 175, and you should get 3.6. Let's check that real quick just to make sure I did that all right. So 630 divided by 175 is 3.6 exactly. So that just goes to show that if you slide two objects down a ramp, they're going to experience the same acceleration as long as the coefficient of friction is the same, and the angle is the same. The next question is question 1 on page 149, which says, draw a free body diagram for each of the following objects. A projectile in motion in the presence of air resistance. Okay, so a projectile in motion is going to be experiencing gravity downwards, and let's say it's moving this direction. This isn't a force vector, this is just showing what direction it's moving. Do not draw the direction that something's moving on a free body diagram and label it motion. That is wrong. I'm just drawing this little dotted arrow as an example. And it's experiencing wind resistance in the opposite direction, so we'll just call this force of friction because it is a form of friction. And it's experiencing wind resistance in the opposite direction. That's it. Because it's not accelerating in this direction. It's actually accelerating backwards. It's moving in that direction, but as we talked about in our chapter on kinematics, something can have a velocity vector and a force and an acceleration vector in opposite directions. That's like when you're coming to a stoplight and you slow down. You were moving this way, but your acceleration was negative in the opposite direction. So that means the applied force was actually backwards, and you're also experiencing gravity downwards, but you're not experiencing any forward force. So that's it. That's your answer to part A. Now, part B says a rocket leaving the launch pad with its engines operating. Okay, so rockets have to accelerate to get out of the atmosphere, meaning they have the force of gravity downwards and a bigger force, that gets cut off, but it's up here. A bigger force, a bigger applied force, we'll call it F of x, upwards. And then part C says a heavy crate being pushed across a rough surface. Okay, rough is just an indicator word meaning that there's friction. So we have our gravity downwards, a equal and opposite normal vector upwards, and we have our frictional force in the opposite direction of motion, and our applied force, we'll call it F of x, going forward. And it doesn't say whether it's being pushed at a constant velocity or whether it's being accelerated, so these two could be equal or they could be in different magnitudes. Again, if your frictional force and your applied force were equal magnitudes, and granted your normal force and your gravity were equal, or all your other forces are equal, so if these two are equal magnitudes, then you would have either a constant velocity or zero velocity, but if they're different magnitudes, then you're going to be accelerating. So the next question is question 2. Let's partition this off real quick. Which reads, a bag of sugar has a mass of 2.26 kilograms. What is its weight in newtons on the moon, where the acceleration due to gravity is 1/6 that of Earth? So if the acceleration due to gravity of Earth is equal to 10-ish meters per second squared, and the gravity of the moon is equal to 1/6 the gravity of the Earth, then the gravity of the moon is equal to 10 over 6, yes, which is equal to, hang on real quick, 1.67. So if you multiply that by 2.26, which is the mass of the sugar bag, you're going to get the force of gravity from the moon, which equals 3.8 newtons, otherwise known as the weight of the bag on the moon. So, and then part B, sorry, this is part A. Part B, that looks like a 9, that's an A. Part B says, what about on Jupiter, where the acceleration due to gravity is 2.64 times that of Earth? So, again, if g of Earth is 10, that means g of Jupiter, 2.64 times the gravity of Earth. So the gravity on Jupiter is 26.4. Acceleration due to gravity on Jupiter is 26.4 meters per second squared, meaning that the force of gravity on the sugar bag on Jupiter is, you know, if I were going to Jupiter, I would bring something other than a sugar bag. Like, of all things, really. Be creative, book. It's going to be equal to 26.4 times 2.26, which gives you about 60 newtons. We get to skip question 3 and go on to question 4, which says a 55 kilogram ice skater initially at rest on a flat skating rink requires 198 newtons horizontal force to be set in motion. However, after the skater is in motion, a horizontal force of 175 newtons keeps her moving at a constant speed. Find the coefficients of static and kinetic friction between the skates and the ice. Okay, so what this means is that the the skater, the first force, 198 newtons, is what it needs to be set in motion, meaning that's what it takes to overcome the static friction. And then the second force, 175 newtons, is what it takes to move her in a constant velocity. In other words, that's what it takes to balance out the force of kinetic friction. So first, let's draw a real quick free body diagram. So this is going to be our force of gravity downwards, which is 55 times 10 is 550 newtons. Our normal force upward, which is going to be equal to gravity, it's also going to be 550 newtons. And for the first part, the static, where she's just getting moving, and she's overcoming the static coefficient of friction, or just the static friction rather, the force applied on her is 198 newtons, which means the force returned, the maximum static force returned, also has to be 198 newtons. So this force over here is equal to our force, our maximum static frictional force, and it's going to be equal to the applied force of 198 newtons, because that's barely what it takes to get her moving. It's just enough to overcome this, so they're equal. So this is going to be our static coefficient of friction times our normal force, because again, friction is mu times normal force, which equals 198. So divide these out, and you get that the static coefficient of friction is 198 over 550, which equals 0.36. And then for the next part of the problem, draw another free body diagram. Same weight, same normal force upwards. God, I can't write today. 550 newtons. But the applied force forwards is, let's see, what is it, 175? Yes, 175 newtons of applied force forward. And it says she's moving at a constant velocity, which, as I've said, means net force is 0, which means all the forces must balance out. So the normal force and the force of gravity balance out. So the forward applied force has to be equal to the backwards force of friction. So that's going to be equal to 175 newtons. So this force, which is our force of kinetic friction, is going to be equal to our applied force, 175 newtons. And again, friction is just our kinetic coefficient of friction times our normal force, which equals 175 newtons. So divide these over, and you get the kinetic coefficient. The kinetic coefficient of friction is 175 over 550, which equals, drum roll, 0.32. Now the last question, which I unfortunately had to start a new page for, is, oh no, sorry, there's two more questions. There's question 5, which says, the force of air resistance acting on a falling object is approximated by the statement that it is proportional to the object velocity and directed upwards. If the object falls fast enough, will the force of air resistance eventually exceed the weight of the object and cause it to accelerate upwards? Explain your answer. So what this is saying is the force, so if you're falling downwards, here's your force of gravity, that your force of air resistance, force of friction due to air, is going to be proportional to, that little fish symbol means proportional to, is going to be proportional to your velocity, which means as your velocity increases, so your gravitational force is always going to be constant. As your velocity increases due to acceleration, this is going to keep increasing. And what they're asking is, can the force of friction due to air resistance ever increase so much that it's actually greater than your gravity, than the force of gravity acting on you? And the answer is no. And the reason why, I'm going to prove this by contradiction. If this became greater than your gravity, so if the force of friction due to air became greater than gravity, then your net force, which is equal to, let's say, your force of gravity, then your net force, instead of normally when this is bigger, when the force of gravity is greater than the air resistance, then your net force, instead of being positive and going downwards, your net force is actually going to go upwards, meaning you're going to start, which would mean that you would accelerate upwards, and your velocity, which is originally going downwards, would start changing and you'd start going up. But if your velocity started getting less and less and less, the friction would decrease. So, since friction being greater than gravity would cause your velocity to decrease, it could never get that high because it would immediately decrease because your velocity would start decreasing. So no, the answer is no. It cannot get that high. You actually reach what's called a terminal velocity, where where these two are equal, and it can't get any higher than that. And I hope that made sense. It's a bit of a long-winded explanation, admittedly. The book says, no, because once at equilibrium, the velocity will not increase, so the force of air resistance will not increase, which, in my mind, is a pretty, I don't know, I guess it makes sense, but it's kind of a lame answer. And question 6 says, the graph in exercise 4-28 shows the relationship between the applied force and the force of friction. And part A says, what is the relationship between the forces at point A, and what is the relationship between the forces at point B? And I'm just going to bring the book under the camera real quick so you can see this. See if I can focus this any better. So, they're asking between the relationship between forces at point A. And cover up the answer. At point A, you have a linear relationship, meaning that the force of static friction is still equal to the applied force, because this is your applied force increasing along the x-axis. Meaning that the object's still not moving. You're still, like, let's say the object is my eraser. I'm still applying force on it, but it's not quite moving yet. And then I overcome that static friction, and it starts moving again. So this is pushing, pushing, pushing. It's not moving. It's not moving. Oh, and then we can apply less force, and it'll still move. Now, at this region, in point B, the force of friction is less than the applied force because it's just kinetic, and so it's going to be constant. Thank you for watching this episode of PHS Physics SOS. I hope you found it helpful. If you have any more comments, if you have any more questions, please feel free to leave them in the comments below, or ask them to me on Facebook, or in the Facebook group, or personally, or over Skype, or whatever, and I'll do my best to help you. The quiz is tomorrow. I apologize again for this being so late. I really didn't want it to be, but I've had a lot of computer issues over the last week, and I finally got it sorted out. So hopefully, I plan to record the next episode tomorrow, so that one should be nice and early, and I hope for that to be the norm and not this. So I hope you can still get some use out of this.